Hello everyone. I want to go ahead and continue with section 5.3. Here we will be looking at, we already looked a little bit at calculate enthalpy changes for various chemical reactions. That will continue to be important in this video. And then the final learning objective, explain Hess's law and use it to compute reaction enthalpies. So we're getting towards the end of this section. And this is actually, in some sense, the most important part of this section, in that we have the information now, the background, to go ahead and do the kinds of calculations that will be important. So we established this idea towards the end of the last video with this idea of standard state as a reference point. I'm not going to read through the definition of that again, but the idea is that we establish something as a reference point with which to compare other chemical reactions. I like to think of this sort of like the way we have defined elevation based on sea level. So we've kind of arbitrarily selected this point and saying we're measuring 0 from here. And so standard state, as we'll see, is essentially about establishing a point where we're measuring 0 from here. So we'll see that as we develop this idea. So we talked about a lot of this in the last video. We're going to talk about standard enthalpy of formation. And this is essentially what we're establishing as our kind of our 0 mark. So the standard enthalpy of formation, and this is going to be important, so I'll go ahead and highlight it, is the enthalpy change for a reaction when you form 1 mole of a pure substance from its free elements. And those free elements are in their most stable states under standard state conditions. So we're establishing, as you'll see, a 0 point here. So for an example, we have carbon plus oxygen to give carbon dioxide. And for this reaction, we have the delta H of formation of carbon dioxide, we're saying is negative 393.5 kilojoules. So we're establishing, to make this compound from its elements, this is what happens. In this case, it's an exothermic reaction. But for NO2, we can see it's an endothermic reaction. So we have a positive value for delta H here, whereas we had a negative value up here. One thing to also notice in this one, we're making the compound 1 mole of NO2. So in this case, again, we need a fractional coefficient to make that work. So what we can do is we can establish a series of enthalpy of formations for essentially any compound, and we'll see why that's useful as we move forward. We have that table in your textbook, and it is in Appendix G. So there's a link to that right here. So what we're looking at here, there's a lot of information, and we're not using it all this semester. We're only using the first column, delta H of formation at standard state. What is delta G? What is S? We don't care right now. We'll care next semester if you come back next semester. But we care about the first column. So the first column is the heat of formation, and that is the energy either released or required to form that substance from the elements in their elemental state. The very first entry on the table is aluminum, which you'll notice has a delta H of formation of 0. I'm going to scroll down. This is a very large table, so we're not going to obviously look at all of it. We have another one that's a 0. What you'll notice as you look at this table, 0 comes up a lot, and it comes up for elements by themselves. Elements by themselves have a heat of formation of 0, and that is basically our sea level. That's what we have defined as delta H is 0 when we have just the elements. And you'll see how that kind of makes things convenient as we end up using this here shortly. But you can basically look up anything else. Do notice again, physical state does matter. So we have, even for aluminum, we have the gas phase. That is not 0 because aluminum is a solid under regular conditions. But this is a really large table, and for the questions that you'll see from the latter half of this chapter, you'll need to be referring to this table for that information, as we'll see. Okay, so let's go back to the chapter. So you'll want to be able to go to that appendix to look up information for most of the questions from section 5.3. Okay, again, we've kind of built up to this idea to develop how to use that table. So there's some examples here of kind of calculating some of that stuff. We're going to skip over that because what we really care about is, I mean, go ahead and look at them, right? They'll be useful. You do want to be able to write heats of formation of reaction. So definitely make sure you know how to do that. But what we want to do, where we're going with this, is we want to use something called Hess's law as a method of figuring out the enthalpies of chemical reactions based on the tabulated information we just referred to. Okay, so let's go ahead and highlight this. Again, probably the most important part of this section is Hess's law. If a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. Okay? This is essentially taking the idea of having a state function and showing why that's very useful. We can take something and rearrange it in any way, add it together, add those pieces together, and come up with what we want. And so what we've done is we've made these tables showing, okay, we have all of these pieces. If we put these pieces together, we can look at how one thing leads to another thing, even if those things don't include the pieces that we're talking about. So let's look at an example here. So we can look at this reaction as one step, or we can break it into steps. So we're basically looking at the heat of formation of carbon dioxide. We can just look that up. Or we could have information about other reactions and take those together to get that reaction. So if we have this reaction, the basically heat of formation of carbon monoxide, and this reaction of carbon monoxide with oxygen to make carbon dioxide, we might see how combining those might get us to our initial reaction. So we're showing that here. We have our first reaction in the two-step process and our second reaction in the two-step process. And we're showing those, and we're basically adding those together. And we can do this in a few steps. So the first step is we just take everything down and just write it as it is. We're not even combining anything. We're taking everything here, we write that down, everything here, we write that down, and then here and here, we write those down. And then we combine things if we can. So we can say 1/2 plus 1/2 is just O2. We have carbon monoxide on both sides. We can get rid of that. And we end up with that initial reaction, carbon plus oxygen to give carbon dioxide. Okay, so this is applying Hess's law. So we're taking these together and we want to get the overall reaction. Okay, so we're adding these together. So this one and this one to get this one. I apologize, the formatting of your textbook is a little bit funny there. I don't know why. This first one should probably be the same font as the other two. Unfortunately, that's not something I'm able to change. So we can show that graphically here in this diagram. And this is a good way to think about it. So we have the enthalpy of this reaction. We take that together. We get this, which is basically creating, when we do that, the carbon monoxide that we have here. And then we have this react with oxygen, and we get this much down to carbon dioxide. So the overall reaction from here to here is the sum of the two parts, from here to here and from here to here. So you're combining those two reactions to get the overall reaction. And we can do this regardless of the path. Okay, so does the reaction happen, in one step like we're showing here, or in two steps as we're showing here. It doesn't actually matter. That's why we care about state functions, is we can rearrange them however we want and get it to work. So regardless of how the reaction occurs, if we start with what we start with, end with what we end with, we will get something that works. Okay, so that's kind of a generic example. There are a few other things we need to mention related to that. And this is actually review. Most of this is review. We did talk about it in a previous video. So the delta H again is proportional to the reactants and products. So if we have, if we have this delta H, and if we multiply it by 2, so we multiply everything by 2, we multiply delta H by 2. So again, we talked about that previously. Also, we can flip it around. So if we want the reverse reaction, if we want to somehow, we're given one thing, we want to add the reverse of it. If we flip it around, we change the signs of the delta H. Again, we talked about both of these things in the previous video, but just to be, just to clarify that as we move forward. There are some examples here of using Hess's law. I would recommend going through these examples and getting some practice. We're not going to do it right now on the video, but these are important things to be aware of. This second one might be a little bit more challenging than you need, but sometimes, doing something a little bit more challenging can help you get to where you want to be. Okay, so I think we're going to pause here. I want you to look at some examples before we do kind of the final application of Hess's law, and that will be our wrap-up video for this section.